Okay, so I actually want to start it off. I want to start off by sort of redoing the thing we did at the end last time, because it's actually a lot more straightforward than I think I presented it. So just to sort of redo what we did last time. So we're looking at the following claim that that if you look at the map that's left multiplication by a matrix, right? So you've got this left multiplication by a matrix, and we look at it from RAT. So A is an n by n matrix. We look at it as going from RAT to RA, and we wanted to show that this is an isomorphism. Right. We wanted to show that the range of A was isomorphic to the range of I'm sorry. Yeah, the range of A was isomorphic to the range of A transpose. Okay. And so there's two parts to that. Right, you need to show that it's one-to-one. You need to show that T sub A is one-to-one, and also it's onto. Right. Okay, so let's do the one-to-one part first. Suppose that U1 and U2 are in RAT, and AU1 equals AU2. Then, just as we saw last time, well, that means that A of U1 minus U2 is 0. Right? And so that means that U1 minus U2 is in the null space of A. Right? But I think as Izzy pointed out last time, it's also U1 minus U2 is also in the range of A transpose. And remember, by the fundamental subspaces theorem, null space of A is the orthogonal complement of the range of A transpose. Right? So this is by the fundamental subspaces theorem. But that means that U1 minus U2 must be 0, and so U1 equals U2. Okay. So that's the one-to-oneness, right? If the outputs are equal, then the inputs must have been equal, right? That's what we call one-to-one. Okay. And then the onto part, right? So right, we want to show that T sub A, the image of T sub A on RA of T actually is all of RA. Right. We want to show that everything in the range of A can be obtained as A of something in the range of AT. Is that notation clear? Right. Okay. That the image of T sub A on RA T is in fact RA. Okay. So well, say you have some vector Z in range of A. In that case, Z has to be A of something, right? A of X, or X in Rn. right? But we can decompose. We have a direct sum decomposition. Direct sum decomposition. Rn is range of AT, direct sum, range of AT perp. But range of AT perp by fundamental subspaces theorem, as we've said already, is the same thing as null space of A. Right? So U can be written as, I'm sorry, X can be written as U plus V, where U is in the range of AT, and V is in the null space of A. But that means that AX, that was our Z, that AX equals AU plus 0. Right? So this thing becomes 0, 0. Right? So what does that say? That says that we found something in range of AT, right? We found something. We started off with something in range of A. We found something in range of AT, such that A of U is that guy, right? So it's onto it. Right. What we get is that TAU is Z. Right. We started off with Z here, and then we found U in range of A transpose. We found a U in the range of A transpose such that TA of U was Z, and that means that we're onto. So that's the isomorphism. I think I said it maybe in too complicated a way last time. It seemed like people didn't really get it. Does it make any questions about that? Any questions about that? Okay, right. Remember, we were trying to show that the column space. We're talking about why the column space and the row space have the same dimension, and it's because of this isomorphism. Okay, so today we're going to do something that has a lot of practical application. It's called the method of least squares. This idea is kind of like the beginning of a whole lot of mathematics. Yeah, and in fact, it's central to the idea of machine learning, to the theory underlying machine learning. So, and it's an application of the ideas we've just seen: orthogonal complement and fundamental subspaces theorem. Okay, so here's the idea. Suppose you have a linear system, AX equals B, right? So you have some linear system. You have AX equals B, but it's overdetermined. Overdetermined linear system. Okay. Remember what overdetermined means? It means that you've got too many equations, right? More equations than unknowns, right? Like you're trying to solve right, you're in R2, but you're trying to solve for the intersection of 3 lines or something like that, right? And so in general, when you've got an overdetermined system, you're not going to have solutions. So unless you're lucky, generally unsolvable. Okay, right? But somebody wants you to solve this system. Of course, somebody wants you to solve this unsolvable system. So since you can't do it, what you do instead is you say, well, I'm going to solve this as best as I can. So you say, so instead, one changes the question. You change the problem to find an x. In the book, they call it x hat. So with this x with this little hat on it. So find x. So A is as usual, and n by n matrix. So find an x in Rn such that ax hat minus b in norm is minimal. Okay. The way you want to think of this norm of the difference is that it's a distance. Okay. So this is really this ax hat minus b is really the distance between ax hat and b. Okay. So right. So you wish you could find something where the distance is 0, right? You'd like something ax equals b, but it's impossible. So instead you go for a different, you change the question and say, well, what's the, can I make this thing as small as possible? Can I make the difference as small as possible? Okay. Okay. The question is, does such an x exist? Okay. We're going to rephrase the question just slightly. Right? Ax is in the range of A. Right? Ax is in the range of A. And so what we're really asking is, can we find somebody in the range of A that's closest to B? So we want to find some P in the range of A, vector P in the range of A, such that P minus B is minimal. And the key thing to remember here is that this range of A is a subspace. Okay. So now our question is the following. If we're in Rn and we have some subspace, S, and we have some vector B. Is there a vector in S that's closest to B, right? So that's the question. Like, can we find the vector? Can we find a P such that the distance between these two guys is minimal, right? And the answer is yes. And what we're gonna use is the direct sum decomposition, right? You can probably guess what we're gonna do, right? We'll take we'll break Rn into S. So the idea to break, decompose Rn as S direct sum as perp, right? And then you break your P into, I'm saying you break your B into something at S and something at S perp, right? And then you throw out the S perp part, and what's left is your P. Okay, that's the idea. So let's see that works out. Okay. Before we do that, let me remind us of the Pythagorean theorem. In the world of vector spaces, so in the world of inner product spaces, it says that if you have two vectors, u and v in Rn, and u is perpendicular to v, then the magnitude of u squared plus the magnitude of v squared equals the magnitude of u plus v squared. Right, you've got some vector u, you've got some vector v, and they're perpendicular to each other, right? And then the magnitude of this squared plus the magnitude of that squared equals the magnitude of the sum squared. So that's just, it's what you remember from childhood, but now in vector space notation. Okay. So here's the theorem. Let S be a subspace of Rn, and be a vector there. Then, one, there is a unique vector P and S, for which the distance between P and B is minimized. Oops. In other words, the distance of B minus any other vector y is going to be greater than the distance between B and P for all y that are not equal to P. Not equal to P, excuse me. Okay, is this making sense right? It's saying that the distance from P to B is less than the distance between y to B, right? So any other if you choose any other vector other than P, you're going to get a bigger distance. Okay, so that's just formal saying mathematically that this distance is minimal. Further, P is that closest vector if and only if B minus P is an S perp. So let's prove it, and like I said, it basically just uses the direct sum decomposition. So you say, well, proof. We know that Rn can be written as S direct sum as perp, right? So B can be split into two parts, which I'll call B sub S and B sub S perp. So where this guy is in S and this guy is in S perp, of course. Okay, and then we claim that B sub S is the P that we're looking for. So P being B sub S is that is the vector with minimal distance to B. Yeah.
Originally then is like same is P the same as X? Like when you initially defined like
P is A of X.
Oh, that like both of them together.
Yeah.
Okay.
Yeah. A times X. Right. Remember our original problem was right to find an X such that this is B. What we're now looking for is we're looking for a vector that's close to B. Okay. Is that okay?
Yeah.
We'll get back to finding X in a second. Okay. Right now we're just saying that what that minimal vector is going to look like.
I think I was just confusing P and B in my brain.
Okay. Yeah. B is the thing you're trying to get close to, and then P is the thing that is going to be close to it. Okay. So we're trying to show that this guy is actually the closest vector, in S to B. Right. Okay. So why is that true? Why? Take any other vector. Take any other vector, V and S. In that case, we can rewrite and then look at B minus V squared. Okay. We can rewrite that as B minus Bs plus Bs minus V squared. So we do something that's a little peculiar. We think we break this B minus V into two parts. Right. We rewrite the B minus V as B minus Bs plus Bs minus V. Okay. Why do we do that? B minus Bs is this Bs perp, right? So this thing here is in S perp, right? Bs minus V, well, Bs was in S, and then V is in S, right? So this thing is in S. Okay. So these two parts, this part and then this part are perpendicular to each other, and so we can use the Pythagorean theorem. So this by Pythagoras is going to be B minus Bs squared plus Bs minus V squared. Okay, so so think what choice of V makes this smallest? Okay, so let me see if I can get us back on track here. So we're trying to show that this. So again, here's your S, here's your B, and by the direct sum decomposition, we know that there's somebody here, which we're calling BS, and there's somebody here that's perpendicular to it, that we're calling BS perp. Okay, and we're trying to show that BS is actually the closest we can get. Okay, BS is the closest we can get, and the reason is if you take some other vector, take any vector V. Okay, take any vector V, then the distance between the distance from B to V squared, right? The distance from B to V squared is this thing here. Okay, it's this number, right? It's the sum of these two positive things. Okay, right? Well, as we move V around, right? As we move V around, this thing we can't really do anything about. The thing stays still, right? But what's the best thing we can do with this thing?
Can we make V BS?
We let V be BS, then this thing becomes 0,
Yeah.
right? The best we can do is to make this 0, and that happens when V is BS, right? So taking V to be BS minimizes, minimizes the distance from B. The distance from B and V, right? And if we take V to be anything other than BS, then this will become positive, and that just increases the number, right? Right. Any other V will increase the distance. Right. And so that's it, right? There is a unique there is a vector, right? There is a vector. It is the vector such that when you subtract off B, you're in B perp. You're in S perp. Sorry. Okay. Does that make sense? Right. There is a unique vector for which the distance between P and B is minimal, right? Any other vector is going to give you something bigger, give you a greater distance. Okay. What vector is it? It's B sub S. Okay, any questions about this? Maybe talk to a neighbor for a minute. Go walk around outside and talk to a neighbor and see if you can formulate a question if you have one.
I want him to relate it back to the original problem. Because I'm like, what is that?
I was just in it.
Yeah.
Like, what was like, I already did it.
It's like going in circles. Because of this, because of this. I'm like, okay.
That's
He's gonna be
second portion.
Yeah,
that's
the
me.
theorem.
Oh.
But we didn't say, like,
That's what I was
I
asking.
thought
I
I
was like,
was
wait.
like just
I
talking
was like,
about
I don't
pieces.
really know
why
we
it
need
makes
it.
sense.
Yeah.
But
That was like the
typically
original
don't-
question. I'm using this to answer the original question.
Yes.
But it's like not actually answering it. It's like answering it to the best for realistic behavior.
Okay.
It
D-
is.
Does, it sounds like there are some questions. Are there questions? No? Really?
We're just discussing.
How does this relate to the like initial problem? of
Yes,
the
we'll
A?
get back to that. So
Okay.
this is the tool. Yeah.
Yeah.
Right now you should be like, we've created this tool. How does this help us with our initial question? Alon.
I wanted to ask, like, if mu and v were subspaces instead of vectors, like, would this like still work?
Would what part work?
Like, would we still be able to find? Actually, wait. I'll just think about this.
Okay. Okay.
Yeah.
How do we know that u squared plus v squared is equal to u plus v squared? Wouldn't it just be like less than or equal to?
That's the Pythagorean theorem, actually, right? That the length of this thing squared plus the length of this thing squared is the length. So here's, right, if you're thinking about vectors, right? This is u, this is v, this is u plus v, and Pythagoras says, that says this thing here. Yeah, it's you don't normally think of Pythagorean theorem in this way, but this is the Pythagorean theorem. Okay. Okay. So what we've just shown is that if you have a subspace and you have a vector in that subspace, then then there is in fact a nearest vector, right? And further, that nearest vector is the thing that you get so it is the thing that when you subtract it off from B, then you get something perpendicular to the subspace. Right? Right. The vector you're looking for is the one for which when you subtract this thing off from B, you get something that's perpendicular, something in the orthogonal complement of the original subspace. Right, that's the statement here. Right? The closest vector is the one for which if you subtract it off from B, then you get something in the orthogonal complement. Okay, so now let's go back to the question, right? Remember where we our rephrasal. So just to run us back again, we were trying to solve this. It was impossible. Instead, we said so here's the original problem. Here's the original problem, and then we said, okay, instead, so we altered the problem. We said, can you find x hat such that this thing is minimal, right? Can you find x hat such that this thing is minimal, right? And then you realize that ax hat is in the range of A. So you change the problem again, and you say, we want to find P in the range of A such that P minus B is minimal. Right? That was our final version of the problem. Okay, but now we've got this this theorem, and the theorem says that we can rephrase that problem again. Our question is then, can we find P such that P minus B is in the orthogonal complement of A, of the range of A. Right, so by the theorem that we just proved, right, we take this problem turns into that problem. Okay, that's the key. That's why we created this theorem. Right. It allows us to change the problem one more time. Right. Finding the p for which this distance is minimal is the same thing as finding the p for which the difference lies in the orthogonal complement of the subspace. Okay, but what am I going to say now?
Subspace theorem.
Fundamental subspaces theorem, right? By fundamental subspace theorem, we can change this one more time. Right? Can we find P such that P minus B is in the null space of A, i.e. null space of AT, right? Yeah, null space of AT. So AT of P minus B must be 0. Okay. Right. So can we find right, right, and this P, remember, is in the range of A. Right. Sorry, I should have. Yeah. Can we find P in the range of A, such as this happens, right? In other words, can we find, so let's start over here. So the question is, can we find x hat such that AT A x hat minus B equals 0? Which is the same thing as saying that AT A x hat equals AT B. Okay, so right, so we started off with this problem. We started off with this problem, which was unsolvable, and it turned out that the best thing we could do with this unsolvable problem is to change it into this problem. Just multiply the whole thing through by A transpose, and that changes that to actually a solvable problem. Okay, right. So this is the method of least squares. Okay. So and then this is solvable. So just solve in the standard way. Using Gauss-Jordan. You possibly get multiple, answers for x hat. So they might be multiple. You might get multiple solutions for x hat, but ax is unique, right? That p is unique. Okay, so let's do an example, just to make this concrete. Well, actually, before we get there, is everybody okay with the changing of the problem? Yeah, Izzy.
So I have a question. Now that we've come to this kind of like final like way to solve it,
Yeah.
are we actually going to be like using the Pythagorean theorem to solve for like the orthogonal complement in that sense, or are we just now that we've like proved all that, we can just go straight to this step?
We can just go straight to this step,
Okay.
right? Because the orthogonality comes into play with the fundamental subspaces theorem, which got us to here, which told us that all we needed to do was to find something in the null space,
Gotcha.
right? Finding something in the null space gives us something perpendicular
Yeah.
to
Okay.
the range of A. So we don't need to do it by hand. It's built into this. Yeah. Okay. Let me make one remark. If ATA is invertible, then x hat is unique. Okay. X hat would be unique. X hat would just be ATA inverse A transpose B. Okay, which is kind of cool, because what that tells you is that, right, in that case, we've created this thing, let's call this thing capital P, ATA inverse A transpose, is what we call the projection map, projection operator. Of Rn onto the range of A. Okay, because what does it do? Like, what does it do? What does this thing do? It takes any B, and then it gives you the that would be X. I need one more A, right? Yeah, sorry, I need one more A. Okay. Because what would this thing do, right? It would take B, and then it would turn, this part would give you the x hat, right? And then you would hit it with A, and that would give you the nearest vector here, right? So what it would do is it would give you, B sub s. Okay. So like it's this thing would take any vector and then project it onto the range of A. Yeah, is it?
If P is A times X hat and X hat has a B at the end, why doesn't capital P have a B at the end?
Say that one more time.
So P equals A times X hat.
Yeah.
And to the left of that, you said X hat is that whole thing, which has a B at the end. So why doesn't capital P equal what that is with a B at the end? Like if you follow the arrow, big arrow you drew, you have P without a B at the end.
Sorry, this is capital P.
But does it not have a B at the end?
No, it's just a bunch of a bunch of
Okay.
operators.
Okay.
Yeah.
Okay, that makes sense.
Charlotte.
Where does the A that you added come from?
So, okay. Okay, so come back to here. Come back to here. So, right. This was solving this gave us the x that minimized the distance, right? Gave us the x that minimized the distance. We said if this thing is invertible, then we can solve for that x uniquely, right? X is going to be this, right? Because then if this thing is invertible, you can just invert it and put it on the other side, right? So then x hat is this thing, okay? If x hat is this thing, then ax hat is the thing that was closest to b, right? Right. So remember what ax hat is. It's the vector in the range of A that's closest to B, right? In other words, it's this guy here, right? It's this thing here. This is going to be the AX. Okay, so right. So right. So maybe I'll come. Let me come back to this. But let me do the concrete example so you guys can see how this actually works. No, actually, let me try and explain it again. Sorry. Okay, so, right, we wanted x such that ax minus b was minimal. Right, we wanted x such that ax minus b was minimal. We saw that that's the same thing as answering the question. ATA hat x equals ATB, right? So to do that, we saw that we needed to solve this, okay? If ATA was invertible, then x would be ATA inverse ATB, and AX would be the closest thing, right? The closest vector, namely B sub RA, right? B sub RA. Okay, so that's where the A comes from, right? This B is going to be B sub RA is going to be A times ATA inverse ATB. Okay, right? And so that's why we call this thing the projection operator. We call this thing the projection operator because what does it do? It takes any arbitrary vector B and then returns you B sub RA, right? So it projects it onto RA and gives you let me call this P of B, right? It gives you this P of B, which turns out to be, the orthogonal projection onto the RA subspace. Okay, so that's why I did this. Yeah, is it?
So capital P is like kind of unrelated from little p?
Yeah, maybe
essentially?
I should call it like pi,
Okay.
capital pi or something like that.
Okay, that makes sense.
Okay. Yeah, it's projection.
Okay.
Normally one denotes a projection onto the subspace. Yeah. So it's a it's just a mapping. You know.
Mhm.
You take your vector, you hit it with the mapping, and it projects it onto
Gotcha.
Rn. Yeah, Ella.
So when we define like that subspace S, is that the same as R of A, like the range of A?
Yeah,
Like,
yeah. So the theorem that we had was just like, if you have some subspace, right? If you have some subspace S, then it's possible to find the closest thing. That's gonna closest thing to B is gonna be B sub S, right? But now when we apply it to the problem, our problem was, can we find the thing that's closest to B in the range of A? So S in that case is the range of A.
Yeah.
Yeah. Okay, so that took a bit longer than I expected. Sorry. So we'll do the I'll show you how it works next time, or not next time, the time after that, because next time we have an example. I hear sounds of terror or panic. Okay, so yeah, I'll try and reserve that room that we had last time, so you have more space.
I have a question.
Yes.
For,
Yes.
for like theorems that like don't have like a name, should we just like state the theorem, or should we just like kind of like for example, like the one we did today, like we did the like P minus B, that's not gonna show up, but if like, for example, it did, like could we call it like the P minus B theorem, or should we just kind of state out what it's saying?
Oh, yeah, I mean, if you can, yeah, that's a good point. Like, I guess generally what people will say is like, because there's a theorem that says that, we can find the minimum vector, blah, 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 and they go from there. But
Okay.
you could, I mean, if you can make up a name that makes sense, then that's okay.
Okay, perfect. Thank you.
Okay, you're welcome.